it's my pleasure to welcome all of you to today's regional school and also to introduce our speaker today, Felix Krahmer, who is currently professor of optimization and data analysis at the Technical University of Münster. I heard Felix has Munich, of course. Oh, yeah, I know, yeah. Very bad mistake. And it's recorded, so yeah, bad luck. Anyway, so welcome, Felix. I heard you have a lot in store for us today, so I don't want to spend too long with the introduction. So please go ahead. The floor is yours.
Yes, thank you very much. Thank you very much for the invitation. And yes, so of course, I don't see any of you, but that doesn't mean you're not supposed to be present and ask questions. You can interrupt at any time. So if anything is unclear, if anything should get more information, then just let me know. And I will give you an overview about a number of different areas that I have also worked in myself, where there's an interplay of structure and randomness that enters the game. And maybe something is there that would also be of interest for your research. So if you have any questions afterwards about how these type of techniques could potentially apply to your problems, don't hesitate to contact me after the short course to discuss. But before, so that's just a quick outline of what I intend to do. Okay, so there's the last, I will start with 4 motivating mathematical problems. Then actually it's 4 problems, but there's only 3 sections because one of the problems will just be very briefly mentioned. And then I will compare. And then if I have time at the end, because I have no idea how, I mean, I could hardly judge how what speed I would get through the slides. I would give you an outlook on some recent things that are related on a completely different problem. But my feeling is that this may potentially be skipped. So let's start with some problems. The first problem that I would like to mention is maybe by now the most established. I think that Benjamin asked me to talk about compressed sensing in particular, so I at least would like to spend some part of this class telling you a little bit of the main ideas, but with the specific focus on the main theme of today's agenda, which is structure and randomness. So let me tell you what is compressed sensing. And I don't expect that any of you has seen any of this, but please, nevertheless, or just because of that, tell me in case anything should need further information. The model behind compressed sensing in its first form is sparsity. So the model, and we will say a little bit on why this is a natural model later on. The mathematical model is to say that you have a signal that has only few non-zero entries. So this is the support, is the set of xi's, the set of entries of our vector x that are non-zero, and this is assumed to be less or equal to s in cardinality, which is assumed to be much less than this capital N. So most entries are 0. You can see this in the this depiction here. You see the colored entries, they correspond to the the non-zeros, and the white entries correspond to the zeros, so that you don't know where these zero entries are, but we assume that most of them are. And then you are taking such a vector, and then you're applying a linear measurement operation. So some matrix A, which is here, which, as you see from the color scheme, we have no assumptions about sparsity or any other things. It's only later on in the context of applications that some structure may enter. Then when you apply this matrix A to our vector X, you get a vector Y. So this is AX equals to Y is the pure problem, but then of course in practice some noise is added, and then the goal is to find X again. Of course, if we didn't know anything about this concept of sparsity, that X has a specific structure, we wouldn't be able to do it because there's many solutions. But the hope is that even though the system's underdetermined, you can exploit the structural information to nevertheless say something about the solution. So applications that motivate this problem are magnetic resonance imaging, for example, or also something that I think you may not have seen before is a problem called coded aperture imaging. The important point here is that the structure is imposed by the application. So if you have magnetic resonance imaging, then you would encounter some type of Fourier measurements, but there are some remaining degrees of freedom. So in the case of magnetic resonance imaging, we don't know how we subsample or what frequencies we measure, and then we also have some design freedom for the apertures. So the question in this particular mathematical problem is, again, how to make use of these degrees of freedom that we still have. How should we design A? How should we choose the matrix such that this problem can be solved in this? The second problem seemingly looks very different. I will try to convince you later on that it's closely related, and it's related to stochastic partial differential equations. And the idea is that we want to find out what they are. So we have a partial differential equation, and we want to find out the behavior of the solution. And that typically goes via some quantities of interest. For example, you could ask for if you're interested in the expectation or the variance or something. This is all part of these questions appear to in the context of uncertainty quantification to some extent. And the problem with this is what do you have at your disposal? You can run a numerical PDE solver, but you cannot a priori run a numerical SPDE solver because there's this randomness in there. And so you can only solve the PDE numerically for a specific realization of these random ingredients. So if we rewrite this problem, I will not talk about this, this is not the topic of this talk, but some of you may have encountered this before. So for example, Cahun and Loewe expansions that you can sort of formalize or capture the randomness in the stochastic PDEs in certain cases via random vectors y, and then here we normalize them to be between -1 and 1. And so we have a partial differential equations where y sort of captures all the randomness, and the rest, this operator A, and the rest that remains is all deterministic. And so then the idea of this approach is to say, okay, we want to understand how it behaves when the randomness changes and the behavior of the randomness. So let's try to sample appropriately. Let's treat the y as a parameter and solve this equation for a specific choice of parameters, and then hopefully be able to say something about these quantities. That's the second mathematical problem. The third one is geometric in nature, and the motivation here would be, for example, when you want to perform a nearest neighbor search problem. So you have a large data set, and you want to, and then a new point comes in, and you're asking which are the nearest neighbors of this points among the data set. And so, or you're asking, is it part of the nearest neighbors of, you have a fixed point and a new point comes in, and you're asking, is the new point part of the nearest neighbors of the fixed point or something like this. And the idea there is, if I could somehow, like, the problem with this is if it's all high dimensional, then these comparisons are costly, because it often requires searching a large space of candidates. And so the idea is, could we maybe reduce the dimension in some way or the other, and then perform the nearest neighbor search in the reduced space. But for that, we need, of course, that whatever we find in the reduced space also has some meaning in the higher dimensional space. And this is captured by this pairwise distance relation. So this A here in the middle is this projection that I said, we projecting into a lower dimensional space. And then I'm asking that the distances after projection that's here in the middle should be very much comparable up to an error of epsilon to the distance in the original space, which is here on the left and on the right. So then, because in the lower dimensional space, which we projected to, you can perform the nearest neighbor search more quickly, then that makes the problem faster. But of course, there's something to consider, namely, if then after projecting we can perform the search very fast, but the cost of computing the projection for all the data points is very costly, then we haven't gained anything, right? So what we need is you should be able to apply A in a fast manner. So we ask question here, how should we choose A that admits a fast transform, and one has this equation. So then you could already see it's again an interplay of structure. We need some structure that allows us to get a fast transform, and then we have some remaining degrees of freedom, because of course there's not just one fast transform, but we have some choice. Okay, so the last problem that I want to touch upon, and this is, as I said, this is only an application, because it's sort of the strategy is really just applying these data projection preserving distances. But I still wanted to point it out, because I think it's a very handy application, and one of the applications where what we are doing here and what I will present to you is very, very useful, is the area of principal component analysis. I think you're all familiar with the singular value decomposition. So then you have a matrix, and you can decompose it into a unitary matrix on the left and on the right, U and V star, and then we have some real diagonal, like positive diagonal matrix in the middle that captures the singular value. And the idea is, the intuition behind this is that it identifies some dominant and less dominant directions of extensions. So if these sigma i's are very large, then the associated columns of V and U signify the directions where the the map has a very large effect, it's dominant, and then when where they're small, it's sort of where it's very contractive. And so basically, if you're thinking about a data set, then these are the relevant directions and the not so relevant directions. So, and if you have a data set, the goal is typically to find the relevant directions. And if you have some parts that correspond to these very small singular values, they are considered as noise, and it doesn't really matter if we find the associated singular vectors accurately or not. Our goal is to find the singular vectors that correspond to the very large component, the dominant principal component. And the point is that the singular value decomposition scales within the size of the full data dimension. So even if you have just very few the principal components that are dominant, you have to transform, do the principal component analysis in full. So the idea is, can we find a way to do this such that we get the large components accurately with fewer computations? So these are the 4 problems that I wanted to use as a motivation. So let's look into them, what these problems have in common. The first is they all have something linear that comes. This is the sensing matrix in compressive sensing. We said, or compressed sensing, sorry, that where we said we're having this matrix A, which produces fewer measurements than the signal dimension, but still it is a linear operation. And then when we sample realizations, that's something that we will see later. It depends on the expansions that you can do with the partial differential equations. You can really interpret it as sampling the parameters, which is also a linear operation. Then for the third case, it's very obvious because we assumed and asked for a projection or for some linear operation under which the distances shall be preserved, and then of course linearity is there by definition. And then lastly, a transformation that helps us to speed the principal component. And another common feature, and that's a sort of a defining common feature in some sense, is that this linear operation is at least partially a design parameter. So it's not that we're asking to invert a given linear system, but there's always something in it that we can choose. And the common question in all these cases is, what is the best way to choose? And the difficulty here is that in all the cases, we're having some dimension reduction involved, like either as the part of the sensing process, where the number of measurements is smaller than the dimension of the signal, or by choice because we want to reduce the amount of computation, and that's why we want to have something lower dimension. And as you all know, every dimension reducing linear map has a non-trivial kernel, and that information is lost. So if your signal that you're having is exactly in the kernel of this projection or map or something or other that you apply, then you're lost and there's nothing you can do, right? Because then you will get 0, and then you know that you are in the kernel, but it could be any vector in the kernel, right? That if you're substantially reducing the dimension, then the kernel will be very large. So what are we going to do about this? And there's basically 2 ways out of the dilemma, and I think we will talk about both of them today. Let's recall the dilemma that it sketches that dimension-reducing linear maps can simplify complexity, but the information corresponding to the kernel is lost. So the first way out is that we have structural information about the data. That was the first case that part 1 that I described to you. we had structural information about the set, and in the sense of sparsity, for example, that I explained in the first example slide. And then we only seek to get good conditioning restricted to the set of interest. So we don't care that there are some vectors in the kernel, as long as we know that these kernel vectors are not aligned with the structural constraints that we have with our data. So there could be vectors on which the map behaves badly. We just know that it's not the ones that we intend to recover. And then, as indicated by the title of the course today, a key tool that we can use is randomness. Namely, randomness provides a means to establish these restricted conditioning bounds, because deterministic constrictions are inferior. It's just that we know that there's a very straightforward way to calculate singular values, and so we can ensure conditioning for a given matrix. But if we are seeking to ensure conditioning on a structured subset of signals only, it's much harder. And then randomness helps, because we can show that we have this desired conditioning properties with high probability, and that's sometimes possible in cases, or typically possible in cases, where we cannot have any deterministic, or where we don't know of any deterministic constructions that would achieve something. And part 2 is some type of a hybrid. I will say something about this, but part 3 and 4, they are more a second way out. This is completely different, because we don't know anything about our data set, so we cannot assume any structural properties, because I said it's an arbitrary point. So if you want to have a deterministic map that maps a data set into a lower dimensional space, then you need to know something about the data set, because otherwise, if I have just one data agnostic dimension reducing linear map, I might as well just choose vectors in the kernel, and then of course it cannot preserve the geometry. So that's why the randomness has the role of transforming the problem. So we had a property that holds for most inputs. So we had the property of, like that is probably true for most dimension reducing maps. The chance of landing in your kernel is very, very small, right? If you think about this, just the kernel is a low dimensional space, so most of the vectors will not be in the kernel. So most of the vectors, whatever most means, because we don't have a measure on the space a priori, but I think sort of visually, I think it makes sense. It holds for most inputs, but that's useless. If your inputs is just a bad one, then it doesn't help. But so that's why we transform this type of problem, this type of idea, and this type of property to a property. We say we're giving up something on a probability of failure. Previously, if we have a good input and a good map, then it works all the time. Now, even for those, for every vector, we're introducing a small probability of failure, but now it's evenly distributed. Rather than completely failing for one vector, it fails with a small probability for every vector, and then that's something that we are willing to accept, because that also entails that whatever my data set is, it works with very high probability. Okay, so that's the quick outline, also the motivating mathematical problems. I will say something about applications in a bit more detail later. So let me pause for a moment and ask if sort of the general mathematical problems are clear, make sense. If you have any questions regarding what I just said. So I don't Let me see if there chat that I. Okay, that doesn't seem to be the case. Then I would suggest that we continue and go into some more detail regarding the first application, and that is compressed sensing. I already mentioned that there will be two motivations. The first one, some of you may not have seen, it's called coded aperture imaging. I think that you know the concept of a pinhole camera. So you have an object, there's this little, no? There's this little hole here. And then the object is projected on the screen by entering this hole and then being turned upside down. And the problem, I mean, why this isn't the concept that we are still using for cameras today is that, as you see, the hole is very, very small, so only very, very limited amount of light gets through. So the quality, intensity, and the quality of the picture is rather bad. And that's why there was the idea some years ago that to say, okay, if we are we want to increase the intensity of the light, why don't we make multiple holes? So the picture is here. You see there's a grid and there's many more than just one hole. But of course, the image that you're getting is no longer an upside down depiction of the object that you're looking at, but it's some blurred version, because it has all, like each of these pinhole cameras is producing an upside down object, and then these are all superposed. Yeah. So that's where we get this imaging plane here. And the idea is why this came up only recently is because, like, when people were building cameras in an analog way, then that doesn't help, because this picture is not what you want, right? So you have then, it has a better quality and higher intensity, but it's no longer depicting what you want. You want an accurate description of depiction of your object. And so, but now that you are introducing computational capacities into the picture, that you're transforming everything digitally anyways, the question was, maybe we gain from this increased intensity, and at the same time, this ambiguities or this different picture can be resolved by computational means. Because if you think about it, you have different shifts of the objects and you superpose them, then what you get is a two-dimensional convolution of your object with the kernel corresponding to this aperture. And the hope then is, because you again having structure, that you could then subsample this and nevertheless recover from this limited information. The task then would be to accurately reconstruct the object from these subsampled measurements. But
just one quick question. So you were only looking for a single aperture. We don't want to use multiple apertures, but just one.
Here is just a single aperture.
Okay, thanks.
And then the question is, how should one choose the aperture, right? Because where should we put a hole and where should we put no hole? And then the second motivation is magnetic resonance imaging. And there, the mathematical model is that the data consists of 2D Fourier coefficients of the image. Again, then the question is, can we subsample to some extent? Or even subsample as much as possible to still allow for reconstruction? And the task is the same: accurately reconstruct the object from the subsampled measurements. but the degree of freedom is slightly different. Here, we said we want to have some type of deterministic subsampling. We want to just take every third, every fifth, whatever signal. So that's not the main design parameter here. Here the aperture is the design parameter, and here it's the subsampling pattern. Because of course there are constraints, and the next step you want to incorporate constraints, that it's that the MRI machine follows a certain trajectory, that it has certain other constraints, but you still have some degrees of freedom running how the subsample, and the question is what's the best way. So the difficulty in both examples is, as already sketched in the introduction, that subsampling leads to an underdetermined linear system. So we need to somehow exploit the structure to reduce the degrees of freedom. And it has already been been spoilered in the beginning that one particular way that can be useful in this context is sparsity. Namely, here I've taken a picture of my research group. And if you see that you do, in this case, a wavelet transform on the right-hand side, you see that most of the pixels, I don't know to what extent it's, I think I can see it. I mean, I didn't do it to the full resolution, but you can see that many pixels in this wavelet representation are black. So, but on the other hand, we of course don't know where this shirt with the pattern appears. That you see in some regions here, there is some significant coefficients just because this this shirt here has a specific pattern, but then of course we don't know a priori. So but we know that there will be large areas where something like this doesn't happen. So for example, his shirt here is less prominently visible. So we know that there are only few coefficients that are significant, but we don't know where they are. So, and that gives us this model that I already sketched up on in the introduction, the model of sparsity. We say we have a basis here with wavelets. We have a signal that has an approximately k-sparse representation in a basis by saying that we can represent it approximately by only a linear combination of k different basis coefficients. But as you see, it's just kj, and we don't specifically say what the kj's are. It's just some, but the important thing is the total numbers. I already mentioned this picture was taken in terms of wavelets, and there's further examples like Fourier, DCT, and so on and so forth. The goal then is to recover a sparse signal from these undersampled linear measurements. The sparse solutions that we're having here, they are in fact often unique. I mean, that's sort of what gets us going. So I think before we go into sort of introducing randomness and trying to have well-conditioned good recovery, let's try to convince ourselves that we actually have a chance, and that's not completely hopeless. So we have to remember here, recall, our goal is to reconstruct a k-sparse signal from linear measurements. So if here we're having the basis, there's always the basis, but we sort of combine it together with some matrix combining measurements, and that will result in a matrix A that now acts directly on the sparse. So we won't discuss so much in the graphical representations anymore. So then that gives us the problem that's depicted here on the right, that we're having a vector X with only a few non-zero entries, and then a matrix that is acting directly on the sparse vectors that sort of has the basis transform included. I mean, this is coming up again and again. It's an underdetermined system. It has many solutions. And now I would like to convince you that if any 2k columns of the matrix A are linearly independent, the true solution is k sparse, then X is really the solution that has the smallest support among all the solutions. So let me try to convince this to you. Suppose, so if the true solution X, so we let the true solution, meaning that we're having X is k sparse, and then y equals A times X. So if the true solution is k sparse, and let's just say we're doing proof by contradiction. If the true solution is k sparse, and it's not this the sparsest one, if not, then there must be a second solution X prime that is also at most k sparse, right? So because otherwise, I mean, if it's k plus 1 sparse, then this is not a contradiction to the fact that X is the sparsest solution, right? Then X minus X prime is 2k sparse. But A of X minus X prime is A of X minus A is Y minus Y. They're both solutions. They both give AX equal to Y. So that's 0. So X minus X prime is in the kernel of A. And that says that, oh, sorry, the columns corresponding to the 2k non-zero entries of X minus X prime cannot be linearly independent. And that's a contradiction because we said that any set of 2k columns is linearly independent. Right? I should say we have made this assumption: any 2k columns of A are linearly independent. But is this an artificial assumption? Maybe to some extent. I'm hopefully later will convince you that it's not. But there are constructions of such. There are such matrices. For example, this was when I took a linear algebra class in undergrad. One of the exercises that I had to do is to explicitly calculate the determinant of a Vandermonde matrix. So if you are taking a Vandermonde matrix with more columns, then each of the submatrices is a Vandermonde matrix with the different parameters. So each of these has a non-zero determinant. So for example, that's why a Vandermonde matrix example for such matrix is Vandermonde. So that's why we are there are constructions, and so it's not a void property or something like this. And then you see that so basically all you have to do in quotations is to say you look for the sparsest solution, and then it's exactly the one that you want. Okay. Yes, maybe yes, maybe not. So the main idea is, of course, to say that if I tell you look for the sparsest solution, that could be is typically a hopeless endeavor, right? Because support size minimization, so looking for the sparsest solution, is known to be a very hard problem in many circumstances and be hard. The other thing is that you may have encountered the Vandermonde matrix that I just used as an example here in a different context, namely as an example of a matrix that's very badly conditioned. So just the fact that all these submatrices are invertible doesn't help us very much, because that as submatrices of a Vandermonde matrix, they will often be very ill-conditioned, and that means that entails then that yes, they are invertible, but as soon as you add a little bit of noise, these properties break down, right? So it doesn't help us for practical application if what we can do is highly susceptible to it. So we need some type of a strong condition on the matrix. But a remarkable fact is that starting with the second of the two conditions, so trying to improve the conditioning of the submatrices, automatically also takes care of the first of the two conditions, as I. So let's try to discuss what it means, what it would mean for the submatrices to be well conditioned rather than just inverted. So, well conditioned means that all the singular values are close to each other. So, if we normalize the columns of the matrix, which is a common thing to do there, then the singular values will all be close to 1. Because if you think about if you have a matrix with normalized columns and you apply it to a vector that is just one sparse, that has just 1, 1 and otherwise zeros, then what this operation is doing is exactly picking out that single column. And so if the norm of that column is 1, then basically at least some of the singular values must be close to 1. And that's why if we normalize all the columns, if we want all of have very good conditioning, all the values close to each other, then the only way where they can be is all close to 1. And that basically means we could say that all the singular values of these submatrices are somewhat between 1 minus delta and 1 plus delta. And when you do that, you end up exactly with this condition here that was first formulated by Candace, Romberg, and Tal. So you see here, let's see if you recall what is the geometric interpretation of a singular value, then you could say it's how much a vector could be expanded or contracted after the application of our matrix A. And if we only want to talk about submatrices, then we want this property only for sparse vectors. So here we have the sparse vectors. And then we're asking that all sparse vectors are either expanded by at most 1 plus delta and contracted by at least, or by at most 1 minus delta. Right? So that's why it's really a condition that says nothing, that is really completely analogous to the condition that we've seen on the previous slide with the invertibility of the different submatrices, except that we have made it stronger and now require condition. And once you have that, as I said, that's one of the surprising facts there. we have only talked about conditioning of the problem, which should a priori imply nothing about how to solve this, but for some reason it also helps to solve. Because if we are having this property here, and again, this is really an analogy. Remember that when we talked about the invertibility in the proof that I presented on the previous slide, we had, because we had the differences between two solutions, there was 2 times the sparsity was the parameter that we had to choose, and that's the same here with the restricted isometry property. And indeed, if we have this property, then we can recover using L1 minimization. We're just taking the solution that has the smallest L1 norm among all the solutions, and because this is this can be rewritten as a linear program, that's why it's something that one can efficiently solve. But I will not talk about this aspect in this presentation so much. I mean, this is a very interesting topic as well. What's the best way to find out that these things are equivalent, and you can get a lot of the geometrical insights as well about these things. But the main thing that I would like to discuss is how to find matrices that have this restricted isometry. Because I gave you this example of the Vandermonde matrix being a matrix that has the property of this restricted invertibility somehow, but conditioning is of course much harder to achieve than invertibility. So that's why it's by no means obvious how to proceed there. But before we do that, let's talk a little bit about different algorithms. And I will just walk you through a number of examples. The restricted isometry property, and that's one of the advantages there, that we have I mean, I've given you an example for L1 minimization, but a lot of different algorithms really use this conditioning structure and can deduce recovery guarantees. This includes something like some iteratively reweighted least squares methods, where you have a least squares problem and you adjust the weights in an iterative manner. Then there's greedy algorithms, orthogonal matching pursuit. I will not tell you what these are exactly. The only thing that I will give you some more details on the next slide is this algorithm by Nidal and Trop called compressive sampling matching pursuit. Oh, it's matching. It should be a T cosam, or that's on the next slide. But also gradient projection, total variation minimization, and there's always a lot of different algorithms that are suitable for different purposes that are probably popping up every now and then. So let's go through one of them in more detail to give you an idea of how this could look like. For that, we need one approximation, like an important step, like an important ingredient in a number of these algorithms is that the projection on the set of sparse signals is something that is very efficient to find. If I ask you, so maybe let's open up the floor, because I've talked a lot, and I'm asking you, for the audience who has been listening, how would you proceed? If I ask you, if I give you a vector here, this is what's here signified as the best S-term approximation. So I have a vector Z, and I'm looking for the vector U that is closest to Z in the L2 norm. So what would be the strategy that you would propose to find this best approximation? Any takers? I don't know.
I think I would just take the S largest entries of Z as the approximation.
Yes, and indeed that's yes. So this is I mean, this is, I think, not very hard to show that this is optimal. And this is, I still want to thank you for pointing this out, because it's something that is not the case in many other applications. So if you have, especially if you have two competing properties in the space of, say, if you're having objects that are low rank and sparse at the same time, then the finding the projection is hardly non-trivial. And but in this case here, exactly doing what you suggested is giving a good strategy. So with this in mind, let's go through this algorithm. First, we start with 0 here, and then equate the current samples to the input samples. So also our iteration counter is 0, and then in every step we're moving it up by 1. And then we can do a proxy by projecting a star V to some vector W. So now this is, then the first step is we can find large entries. That's exactly what you just said. And we can find the projections of the large entries, look at their support, and that take this support set, then take the union of the new support entries that you found with the old ones that you had. With this new modified support set, you are doing some type of least squares approximation. With whatever you find on this vector here, you're taking the best S-term approximation and then entering it into your signal Xc. And then you're looking at the residual V, and then you're trying to approximate the residual in the same manner. The idea that's behind why we're doing this approximation here is that we know that our matrix A has the restricted isometry property, so it performs very well when it's acting on sparse vectors. And so that's why we're going to the best S-term approximation and then restricting to these sparse coefficient sets. The conditioning is very good. So that's why we know that there's some amount of invertibility. So that's the main idea here. I mean, I'm not going to show any details about the proof, how this works. I just wanted to give you a more iterative algorithm so that you have an idea of how these things work. As I said, the main topic will be how to find matrices that have the restricted isometry. And let me recall the observation that I've already talked about, that basically it's really about restricted conditioning. A matrix A has the S delta restricted isometry property if all singular values of all submatrices of S columns of A lie between 1 minus delta and delta. That's so. Yes, let's pause for a moment. And if I think that property before looked very natural and didn't look very impressive. And I personally feel that if you formulate it this way, all singular values of all submatrices of S columns, this suddenly sounds like a much, much harder and more difficult property to fulfill. Because if you think about it, how many matrices are there that have S columns and that are submatrices? Then it's N choose S. And then you already see immediately that it's impossible to show them, to check them all. So like, if we are interested in the scenario that the vector is much sparser than the dimension, so N choose S is very, very large. And then you could think there are some tools that are available in linear algebra on finding singular values, eigenvalues, and stuff like this. One thing that may come to your mind, so if you haven't seen this, I'm not going to spend much time in the details. If you haven't seen this, just ignore this for the moment, it's not necessary. Some of you may think of this, that the Gershgorian circle theorem could be the tool that can be useful for this, but actually one can show that this leads to suboptimal embedding. So that's not the right tool to do. And the way out, I mean, I promised this to you, so we have to get to this punchline at some point, is randomness. And let me give you a brief idea of what's the strategy there, why randomness is helpful. Because randomness allows us to focus on a single submatrix of S columns. So if we are saying the probability that any fixed submatrix of S columns has typically has all the singular values inside in this interval, or in other words, the probability that any such fixed S-column submatrix has a singular value outside of 1 minus delta and 1 plus delta is very, very small. So the probability is at most eta times n choose S to the -1. And then with probability at least 1 minus delta, 1 minus eta, all singular values of all matrices lie in 1 minus delta and 1 plus delta. How does this follow? So the idea is that we follow a union bound. We are thinking that we're considering all these events. If we're having n choose as submatrices, and then each we define the event that this particular submatrix is violating the property. And so then the total event that some submatrix is violating this property is the union of all the events, and then the probability of the union is less than the sum of the probability of the individual events. And that because each event has a probability like this. So if we're summing this quantity here over all the n choose S events, you're getting eta as the probability of failure, or 1 minus eta as the probability that all the singular values are under control. So let's pause. I don't, as I said, I don't know anything about your particular background. So as I said, invite you to interrupt and ask if anything of this is not clear to you. So now let's proceed and think about what to do next. We now want to do singular values of a random matrix, because we have just showed you if we know something about that the singular value of a random matrix is under control with high probability, then we can also get the restricted isometry property. So now we have to find out how to do this. I mean, I'm citing Baranyuk et al., but this had been around before, so I'm not able to list all the references here. So that's let's look at how this submatrices of S columns look like. So they are let's call them AS. We have fixed some support set S, and now we're restricting our matrix A to that set of columns. And then we need to estimate the singular value of AS. And as you know, the singular values are the square roots of the eigenvalues of A star S times AS. So that's why we need to estimate these eigenvalues. And of this quantity A star S times AS, we can take the expectation, and that's of course something that really depends on the matrix. But if, for example, if we have independent entries, or in many cases we have something that's called isotropic, and that means that we can normalize the matrix such that all these A star S, AS matrices have expectation identity. So we have this quantity A star S, AS that we want to control, and we have the identity So in order to bound the singular values, what we need to do is we need to estimate the deviation from the expectation in the spectrum. So I don't know to what extent the spectral norm is clear to everyone. So let me see. Let me just say the notation may also not be fit. This is the supremum x in the unit sphere bx in the L2. This is, and now the important thing is that we have this, and we have an additional property. So here what I've just shown here is the definition. Is for any matrix B, you can say that the spectral norm has this form. But here we have something in addition, namely the matrix A star S AS minus identity is also symmetric. And for symmetric matrices, so basically I could continue for arbitrary matrices here, X and Y, if it's a square matrix, let's assume it's square, then we have, I can also represent, then we have Y BX. Right, that's just I think Ries's representation theorem or something that the dual definition or dual way to define this L2 norm. But the important fact that we will be exploiting is that for a symmetric matrix, we can choose Y equals to X. So then we get this quantity. Yeah. So does this make sense? Is this something that you have seen before or that you're familiar with, or you want additional explanation? So does this mean it's clear? I don't know. I have. Okay.
There's a chat answer.
There's a chat answer. Okay. Thank you. Very good.
So at least somebody's listening.
Somebody's listening and somebody's fine with it. That's good. And the idea is that we can now proceed similar to what we've done. We want to do a union. So we can, when we have a fixed X, then we can potentially estimate this. Not so difficult, and then you could do a union. I mean, I'm not going to talk about this particular part, but that works. And it's just some, if you put a fixed X, then it's a random object that has been studied and that's well understood. If you know the matrices, that's not, I mean, standard techniques. But the problem that's not so familiar to many of them is wait a second. We just said we want to do, we have an X in the sphere and we want to establish it for a fixed X and then do a union bound. But how can we do this? Because there are infinitely many X's. So how can you do a union bound over infinitely many things? That means you have to add infinitely many probabilities and then you're screwed, right? And the idea that shouldn't surprise you is that you have to somehow discretize, but how you do it, I think I will show you on the next slide. The concept that's of importance here is the concept of covering numbers in epsilon nets. An epsilon net with respect to some norm is a set such that, I mean, this is an abstract definition, I'm reading it out, but I'm drawing a picture in a second, that for all X in this set S, there exists Y in our net, such that X minus Y is less or equal to X. So let's try to do this. Let's draw a set. take this annulus here, for example. Okay, this is our set. And let's assume, let's start with just some point. And let's assume the radius is like this. So basically, then with this point, that if we add this point to our epsilon net, then all the points that are in this ball around it are covered, because what we require is that all point in our orange set must be epsilon close to some of the points. We have defined one, so we don't have to take care of those anymore. So now we could proceed and just make another point that is not covered and draw another ball around it of radius epsilon and stuff like this. These are not all the same radius, but I think hopefully the idea is clear that we are drawing balls of radius epsilon and asking how many balls of radius epsilon we need to cover our set. And this is something that there is also results about. For example, if you have units, like in the case here, we are looking at when we're restricting to one particular support, all we need to cover is the unit sphere somehow, and then this is known exactly how these covering ends look like, up to some multiplicative constants. And then this discretization is in fact sufficient. And that's, I think, one of the key features here if you want to understand problems in this context here, and that's the so-called covering argument. And I'm going to show you this for this particular matrix here. We have a matrix B, and B here, if you go back, is A star S, A S minus identity. And then this is what we wanted to estimate, right? The supremum of X in S minus 1 is of this inner product. And then for some reason up to this prefactor here, we can estimate this using the supremum over the finite net. And let me show you exactly how this works. So, but before I do that, let me ask you, is there another question in the chat? No. For some reason. I don't know I cannot see the chat. Was there a question? Sorry. Is anyone?
So far the chat is empty.
Okay.
I think people are very shy, but
that's fine. I mean,
it's one of the big downsides in Zoom. Yeah, I used to stare at the people in the room till they all say something, but it's not possible.
That's difficult today. But yes, yeah. I can only repeat that you should feel free to interrupt. And because this is, I think, the crucial part, because this is something that I find very remarkable, that you can reduce this infinite supremum to a finite supremum. So we said, and I have already asked, that it seems to be at least okay to one person that this spectral norm is equal to the supremum, the inner product. So if it's equal to the supremum, then it's a compact set. So that it needs to be assumed. So we can start by choosing some x in S minus 1 such that A is equal to, oh, sorry, B, of course, equal to Bx. and choose y and epsilon, which approximates x as x minus y2 is less or equal to. So we have an epsilon net. So in particular, this maximizer can be achieved in all cases. So by the triangle inequality, we have ax x minus ay y is equal to, so let's introduce some terms, cross terms here, x minus y plus ax minus y. So if you think about that, here we added ax, so here we added ax in a product with y, and here we added ax in a product with minus y. That's why it exactly cancels. And this is now where the triangle inequality comes in, because we can split the two terms here. In the first term, we are, oh, sorry, I'm, of course, b. It changed last moment from A to B, and to avoid confusion, and hopefully I will not introduce it now, because now we can say this is the norm of B times X. Here we take this, and we're using the definition of the spectral norm and Cauchy-Schwarz. So we have B times X, 2 norm, X minus Y, 2 norm, plus B X minus Y, 2 norm, times Y, 2 norm. And here we're using effect. Let me go back one slide. In the definition that the covering the net is part of the sphere, right? So when we're having this here, y's are part of the sphere. So this is equal to 1. This is equal to 1. And this is less or equal to epsilon. This is less or equal to epsilon. And then the full thing is bounded by less or equal to 2 epsilon b. And the trick is now, let's try to see, a y. Y is greater or equal to a x minus 2 epsilon.
Yeah, A is back instead of B.
I just said, thank you. Ex minus 2 epsilon b. And this is, now we can see that this here we said by definition x was chosen such that this is the spectral norm of b. And that's why this is 1 minus 2 epsilon b. And this completes the proof, because we can just divide, like if we found one particular y that's larger than this, and so the supremum certainly also needs to be larger. Okay? So I think this is really at the core of the proof here. And that yields one particular fact, that Gaussian or sub-Gaussian matrices have the restricted isometry property. So, but first of all, before we go is there any questions with respect to this proof? So I could say, I haven't said, if you want to read up on this, C, E, G, so there's a book, a lecture notes by Roman Verschiedene and random matrix theory. Where this is covered. But there's lots of references. I mean, this is all standard. And yes, so let's try to see how this works. And so we can now define something general called sub-Gaussian random variables, where you have a sort of a tail decay of the random variable that's below the one of the Gaussian. But if you haven't seen this before, just think of a Gaussian random variable, or even simpler, a plus minus one random variable, taking both with equal probability. And then we say a matrix is called sub-Gaussian with parameter C if all its entries are independent sub-Gaussian random variables with parameter C. And so we had this the strategy that we just sketched, and that leads exactly to the following result. We have an n by n sub-Gaussian matrix with parameter C, and then we have the restricted isometry property with high probability. For some parameters, some complexity here, and that's here. And now the important thing is that it can be shown that the embedding dimension, the necessary, so the embedding dimension looks like this. So up to this constant, it's optimal. I mean, I think if you haven't seen this technique before, just doing some type of covering and like taking a very dense set of points and then estimating the matrix independently on all these points seems something that is seems very suboptimal, right? Because why would, I mean, it's such a simple technique, but nevertheless, what you get is a near optimal embedding dimension. On the other hand, if you are want to follow a deterministic construction, so I've already said, I mean, now I can tell you the Gershgorien theorem yields something suboptimal, and in particular you get S to the S squared, rather than here we're having S, and for Gershgorien and stuff like this you would get S squared, and the best known is very close to S squared, S to the 2 times minus mu for mu as small as 10 to the negative 24. So S squared for all practical purposes. So that's why it's remarkable that such a simple proof techniques that I think I've been able to convince you, or hopefully get the gist across to you in the last hour or so, is able to establish something with high probability where no deterministic construction is known that it comes into place. And so this is, of course, there's no reason to say that there shouldn't be a deterministic construction. It's possible that there will eventually be, with the help of some number theoretic tools or stuff like that. But it's important that it's apparently very complicated. And here the proof is very, very simple. Let me quickly revisit now the structured scenarios that I have mentioned in the beginning, now that we know about Gaussian matrices, because of course no MRI machine will have a Gaussian measurement ensemble included. So if we are recalling that we talked about these coded aperture imaging modalities where you model things by 2D convolution, And then one way to make this precise is to choose your vector epsilon at random with these sub-Gaussian entries, like in particular plus minus 1. If you say like either it's open or it's not open, it would be 0, 1, but then it's not centered. You can center it, so it would fall in this category. And so then you're taking this convolution. And then, as I said, we want to subsample and in a deterministic way. So we have something P omega coming into the game, and the measurements are looking like this. And this is something that I personally have contributed to earlier, so that's why I know these results. It's what we get is something similar in S, but because of the structure, it's a little bit worse, the dependence in the logarithmic factors. There's nevertheless, of course, in addition to the application, it has advantages that it has fast matrix vector multiplies. Because of you can write it in terms of Fourier transform. It has this reduced amount of randomness, which is often also preferred, and it has an efficient realization as a filter. The second example for the motivated by magnetic resonance imaging is can be modeled via the Fourier transform, and for that we have the discrete normalized n by n Fourier transform that is given like this. So we like the non-normalized. So we don't have a normalization factor here, and then again we restrict it, but this time we restrict it at random, and then we can have a high probability. So I've listed here this reference with log cube. Actually, it has been improved to log squared by Habib and Regev. So again, you need some amount of additional logarithmic factors with similar advantages and many applications. The thing is, something that I have neglected on the last slide is the basis, because I said in the very beginning that of course you have sparsity in a particular basis, which we incorporate in the measurement matrix. So here we haven't incorporated it into the measurement matrix. And going back to this random convolutions, I must say that incorporating reasonable basis matrix is something that is still open. I think it hasn't been done. It's very difficult. But for Fourier, this is possible. You can, there's a way out, because if you have, say, sparsity in wavelets or something like this, then you should not choose your frequencies independently at random, but follow a variable, so-called variable density sampling. Let's say a word about the proof. So variable density means you choose different frequencies with different probabilities. So let's talk a little bit about the proof structure for these structured random matrices. It's suddenly, because we have less randomness, that means if we have x1 approximately x2, then having these different measurements xa, x1 and x2, they are really like even further from independence than in the Gaussian case. That's why in this case the union bound is indeed suboptimal. So I will not be able to present you a proof in this short course here, but I think I can draw you a picture. Because how do you proceed is a technique called chaining. So you first start with one x0 and establish the result for this x0. Then you continue with a reasonably small sized but equally distributed subset. Let's put it like this. And so in this case, you don't have to establish the property for all these points individually, but you only need to look at all these differences here. So if we have x0, and we recall that we have a linear operation. So if we have x0, the property for x0, and we have the property for the distance, and sometimes in certain circumstances you can infer that it also holds for all these points. And then in the next step, I'm only doing it here, you're doing a much denser set of points, but then you only have to get the distances to the closest point. And then basically in the beginning, so let's say that this is chaining. Union bound over few larger probabilities, or let's call them events. Later, many small events. So the idea is that these points in the resolution in the different steps, that increases quite drastically. So in the beginning you have few points, but then it grows very fast. And at the same time, because there's so many points and you already have a quite fine resolution, so doing the next step is only a very, very tiny step. And that's why you get very small probabilities, which you make the better reason to control. I mean, this is no way that you can understand the proof, but maybe it can be an intuition if you ever encounter these techniques that you sort of have an idea of what's going on. And I will, in the next part, try to explain or give some intuition of how the things that we have just seen can actually help for stochastic PDE, or even though the things related to uncertainty quantification in some extent. So let's recall the setup, and I'm already jumping into the reparameterized setup. So we have stochastic partial differential equations, and we're treating the random inputs as parameters. So because we want to sort of find out how it behaves in terms of the randomness, and so that's why we have to fix certain sampling points. So because if we have this expression here and we understand how the solution behaves as a function of the parameters y, then we can also, of course, deduce what happens, or maybe with some further thought, deduce what happens when we choose y. So, and we will particularly care about some quantities of interest that are real valued here, such as the expectation. And then for a solution, well, the expectation or some other quantities of interest, because the expectation wouldn't depend on the randomness anymore, but still the point is, for if u equals u of y of the PDE is the solution, then we want to also express the quantity of interest as a function of y. So now we're coming to the Carhoonan wave expansion that basically says that these quantities of interest in certain scenarios that I will not discuss here in detail, such quantities of interest or solutions in general can admit some approximately sparse expansions. And the important fact is that this involves a product basis. This is this T here. And I would say down later here how exactly it looks like. And we have this basis of basis vectors with multi-indices Tn, and we have coefficients Cn, and then f of y is the sum of these coefficients multiplied with these basis functions of y. And the important observation that I think one can motivate via the theory of certain partial differential equations is that this expansion is indeed approximately sparse in certain cases. So we have an approximation by a sum of indices that are only in some predefined index set S, but unknown. And then for n in this S, that is relatively small, the Cn are the associated coefficients, and then the remaining coefficients are approximately z. That model clear? I don't know to what extent you are familiar with this theory, but I think that for now it's okay if you just accept that this is the model. So basically,
so we don't know the S.
We don't know the S.
Yes. Okay, that's S. Okay, good.
We just know that when there is a certain set, like often, like sometimes you have certain additional assumptions or something, or like some additional model things that you know about it. For example, in a number of applications, these S are known to be downward closed, which means that sort of if I have a certain index that is active, then all the indices between this index and the origin are also active. But because we are in high dimension, this still leaves a very large number of potential configurations which we couldn't just try out. So, and then the important thing is that we have this product structures in high dimension. So we are having one-dimensional basis functions. So, for example, Fourier, as we've discussed before, or some type of orthogonal polynomials. And then this complete basis functions are tensor products of all these basis functions over all the dimensions. So if you're putting in this input vector y, then basically you're taking each component and plugging it into one of these component, these one-dimensional basis functions, and that gives you the high-dimensional basis. Is that clear to some extent? So I think what exactly they are will not be relevant in the presentation that's coming up, because I'm not going to talk about, like, I'm sort of really complementary. In the first part, we talked about why a certain matrix has the RIP, and here I would just sort of say, with similar techniques to the morning, you can show that, and then sort of that's somehow all hidden what these TNs are in the precise range. So the importance, why does the RIP is relevant? Because we said we have this sparse vector here, so we can write it all in a vector, and then it happens that the vector is such that C1, the first entry, is multiplied with the first T, so this would then the second with the second, and so on. So this is really one row of this matrix multiplied with C corresponds to one of these approximate function evaluations. So we have our coefficient vector. We know that f of y is approximately this coefficient vector multiplied, and each entry of the coefficient vector is multiplied with the respective basis function. And here the difference is that now we are not having just the sparse coefficients, just the non-zero coefficients, but because we don't know them, so we're having really n to the d coefficients in a capital D dimension. So these are a lot of the coefficients of the C will be non-zero, but we don't know which ones. And then we are doing this for one y, y1, we're doing it for another y and another y. These are the samples that I mentioned. So that's giving you f of y1 is having this expansion here, C multiplied with this vector, And because F in general has this decomposition, the coefficient vector C is the same. That's why it admits such a matrix vector representation. And we call this matrix phi. Yeah, this is a lot of notation, but maybe you should think about it in this representation here. So we can have a function, we can represent it in terms of a certain series of basis functions. You get the coefficients, and because these coefficients do not depend on y, only the basis functions do. That means when you're taking this multiplication here, coefficients times basis functions, the coefficients are the same no matter what y. You plug in. And now you realize when it takes a moment to write it down like this, but now you realize that we're back in the business that we've discussed in the last 1.5 hours, because we have a vector that's approximately sparse. We have some matrix with some degrees of freedom that we can choose, because we said we can only evaluate we can numerically solve our partial differential equation for a fixed set of parameters, but here we could just decide to solve it at exactly these locations, and then we will get the solutions f of y1, f of y2, and f of yn. Yeah, because using that, the quantity of interest is a real valued thing. So I think that's important. So let me pause and give a chance for people to speak up if they would like us to repeat. And because that, of course, that's sort of the crucial part for what's going to follow.
So even though the y is our random input, now we can choose it to our purposes.
So basically, we haven't said anything about random here, right? So this is just, the idea is, this is our quantity of interest.
I had the stochastic PDE in
Yes.
mind, and this has random input or some randomness, and this was...
Okay, that's good that you're asking, because the idea is we have a stochastic PDE, and we want to understand the stochastic PDE. But we cannot simulate, it's more difficult to simulate the stochastic PDE. So we write this, this representation like this, where y is the random input. And now we're plugging in deterministic, like a priori deterministic things for y, and hoping that we understand the behavior of this quantity of interest as a function of y, which then would also allow us to understand how it behaves when y is chosen at random. It's very interesting, because in the end we will choose it at random again. So we're going in a circle. But at this point here, we have reduced the random the random object to a deterministic representation using this this expansion. So now that's why you should think of, we have I mean, I'm not an expert of how to solve numerical PDEs, but it is possible to if I fix y in any way I like, it is possible to get an approximate solution of the PDE, which then allows me also to get an approximate value of this quantity of interest. So, and then I can, if I do this for y1, y2, and ym, then I get quantities of interest f of y1, f of y2, up to f of ym. Right? So far, everything deterministic, everything in our choosing. But the point is, what is similar to what we've seen in the morning is there is a lot of structure. There's these Tn's, which I have no control over. They are sort of given to me by the differential equations. But these Yn's, for which parameters I do my evaluation, is up to me. And there the randomness comes in. This has been proposed by your colleague Holger Rahut in Aachen, and a lot of others, including Christoph Schwab and Ben Adcock, Clayton Webster, and many others. they were really picking up on this and following the ideas that I've sketched to you in the first part of the talk, namely saying, if we choose these y's at random, then we hopefully have a good chance that this object here has the restricted isometry property, and then I can use compressed sensing to get this vector C. Okay. So the result would then, so for example, then we could use L1 minimization, OMP, like all the algorithms that I've just sketched to you, and we could recover. So, and then what, if you put it together in sort of a prototypical result, we have a number of measurements. We said you can, using randomness, you can do linear and S here, and then you have some logarithmic factors that depend on a lot of things. And we could even say, for all we care about, because the bad part is the D in the exponent, right? So as long as everything is polynomial in all the objects here, we are happy, right? So the problem is this matrix here has M to the D. N, okay, I switched notation from N and M. This should be the same, sorry. This matrix here has an exponential number of columns. And so the idea is that the number of samples that you need to choose, that should not be exponential, because if you need an exponential number of samples of PDE evaluations, then you are not in good shape. And so that's why we are very happy here that we are having M computation called PDE solves, and M is polynomial in all these quantities which are under control. Right? So far, so clear. And however, if you are very careful and have a look, then you also realize that you need to do the second step here. And the second step is the inversion of this matrix. So even if you are using compressed sensing techniques like L1 minimization, you are finding a vector of minimal L1 norm whose length is exponential in the dimension. Right, so it's exponential indeed. So even though the number of samples is very limited, the reconstruction procedure is very costly. So that's why I think what I will give you some ideas about is how to overcome this part of the problem, and also make this part polynomial in all the different parameters. So that was something that, at least in these first works here, was not really considered in detail. Okay, so let's start by revisiting an algorithm that we have already seen and see where the problem is. Right, so this is exactly the same algorithm I just translated that I've shown to you in the first part, COSAMP. And I have just translated it to the new notation because now we call things U and phi and C rather than X and Y and A in this context of PDEs here. But other than that, it's the same. So let's have a look of how costly the different steps are that we do. So first of all, the trivial initial approximation is, I mean, setting something to 0, something that we can do. Everything that's O of M is fine here. Merging the supports when things are only of size S, all that we can do. The only thing that are critical are these two operations here, where we have V and we are applying the complex conjugate of a measurement operation, because that really expands the thing and gets a very long vector. And then if we are having a very, very long vector and want to identify the large components, even though, I mean, that's a question that I asked earlier, and that you told me that this is, in theory, easy to do. You can just keep the largest entries, but still, if you have a vector that is of length n to the d, that will take an exponential number of operations. So these are the critical parts, and these are what we will discuss now, how to replace them in order to make things a little bit more efficient. Still, of course, the idea is to somehow build upon the algorithm cosine that was there and also part of the proof. And this, especially just the support identification, that's these two steps here where we project, and that is the things. And so this is what we will analyze in more detail, and for everything else is under control. And I think you can think about how to do it most efficiently using conjugate gradient stuff, but that I'm not going to talk about in more detail. Okay, so the approach that I will talk about now, we have to somehow use the product basis structure, because obviously if we don't have anything that has at least building blocks that are of smaller size than this exponential, then there's nothing we can do. But in order to make best use of it, we use some additional sampling, and then this can be done better. And it's important, just an important side effect, that we don't really use the exact nature of these system here, except that they need to satisfy some orthogonality condition, and I think so that includes some orthogonal polynomial that are also used in these applications. Yes. So that the thing is that this k, the bound, somehow appears in some suboptimal fashion. So it's really optimal if k equals to 1. So then otherwise, like the k can appear in some higher dimensions. But still, it's much faster also in practice as compared to just running a regular L1 or cosine, L1 minimization or cosine. Okay, so we should say, and we've already talked about the price of randomness that we have here, but here nothing is for free. We can make things faster, but we need some additional samples to really fine-tune all the different steps. And that's why we are no longer having the linear behavior in the sparsity, but just polynomial. But, and for k greater than 1, we're having k to the 4d, with d is something that's not quite the dimension, but it's a quantity that in certain circumstances can also be smaller, but I will not talk about this in more detail. So let's give you some idea of how this works. The idea is somehow that we need to, of course, do it entry by entry. So we are in a high dimensional space. So each basis function is identified by a multi-index. A multi-index that has d different entries that are all integers. The idea is that we identify these d entries individually. So here, how does this look like? So for example, we're looking at the set here, nj, which is the set of all the jth entries. So we are asking if we're looking at the active entries of our vector C, basically we're asking if C and K is active, then nk is a vector of length d of integers, and we're asking is its jth entry H. So I think this is a little bit difficult to grasp. So let me, another way to write it down is you take all the active nks, so all the nks such that C of nk is non-zero. And then for each of the vector, you take its jth entry and you put it into the set. So basically, you will have then a set of all the jth entry, and that's your set nj. And if we identify the set nj, or the set n1 say, then we know that for all the active coefficients, or for all the active indices, the first entry must be one of these numbers that we have in our set n. So here we have pointed them out. These are all the candidates. These are all the candidates for the second entry, and then third, and so on unto the dth. So this is the first step. We learn these entries that appear in the first position of the active indices, the second, and so on. And now we have to build up the indices from them. And there's a lot of potential combinations. And if we're just looking at all the combinations of one of these, and one of these, and one of these, and one of these, then it's still exponential. So we have to reduce it even further. We have to find out if we're looking at, we know that this number here somehow appears in the first position of the index vector corresponding to some active coefficient. So what? It could be one, it could be more. So which second indices correspond to this first index? So we have to pair. So it must be something of this, because these are all the second indices that appear. So this one, for example, is paired with this one. So we know that these two appear together, and this index does not appear together with any other second. That's the step pairing. So we're starting with the first index and then building them up step by step. So, as I said, one way to rewrite the set nj is this here. We have all the active indices that are in the support set. They are of the form n1 to nd, and then we're singling out the jth entry and then putting all the jth entry that appear for some active coefficient into our set nj. And then j obviously has a special role. So now we have to somehow use randomness, or we want to use randomness. And so let's say the jth entry we don't select yet, but we select all others at random. So all others entries are selected at random. These are these yjls. And you see here that the jth entry is left empty. It's left as a dot, so that we haven't selected. But we're looking at this as a function in this particular random variable, and then we want to find out, if we're going back to the product representation. Go back to the product representation. So where they are introduced very much in the beginning. Here we have the product representations. So we're looking at the jth factor, and we want to identify the jth factor. So we want to find out, is the jth factor one particular polynomial tj nj, or is it a different? So that's why we are using the randomness in all the other coefficients and leaving this empty. And then in this particular coefficients, we're taking the inner product with tjp. So we're asking, is the polynomial in the tensor product format that appears in that particular variable TJP or not? And for that, because if you think of that everything else is selected and this varies here, taking this inner product, then we expect that it's 0 if P is the true coefficient, if it's 1 if P is the true coefficient, and 0 if P is not the true coefficient. But now, what we're doing is we're repeating this n times. So we're having not only FJP, but FJP with an L. So we're having FJP1, FJP, and so on. So we're having really a number of different instances. Because then, this blue thing here, because we've chosen them at random, these are the coefficients of a RIP matrix. Now we are really in the form of a compressed sensing problem. We're having these things that we calculated as an RIP matrix with some vector that we multiply. And this thing is obviously sparse because it's the sparse vector that's pointwise multiplied with something that makes things even sparser because these things tend to be 0. So what we get is that the 2 norm of the vector that we observe is approximately the 2 norm of the vector Cn multiplied with this inner product. And this is very good now because this inner product basically asks us which coefficients are active and which are not. So if P is not among the active coefficients, the right-hand side will be very small. If P is among the active coefficients, we will get out the respective Cn, and that's why this can be identified. So that's sort of the gist of the idea. I will not go into the exact details here, but I will just point out that in order to do this, like now we have a 2 norm. So what the question is, how do we identify, what's the best way to identify whether the 2 norm is approximately 0 or not approximately 0? It's a nonlinear function, so it's a little bit more difficult. And here we're using randomness again by multiplying the entries of this vector with these random Gaussian coefficients, which is actually a way to mimic the 2 norm. Because if you're having, let me write this down, if we're having the expectation of the sum of GI AI squared, this is equal to the 2 norm of A. So the 2 norm can be mimicked by a sum of Gaussian random variables. So that was just an idea. I think this is maybe a little bit hard to follow in the exact details, but I hope that the idea that we are choosing one variable as the things where the direction where things happen, and then sampling the other variables at random to use the RIP, hopefully was getting it. So let me write it down to the in this form here. Entry identification. So what we do is we sample our function f. We want to output this entry identification set nj, and then we basically calculating this quantity here that mimics the L2 norm, and at least with a certain probability, and that's why we apply the median, because if it's with a certain probability behaves like the L2 norm, taking the median would only give you 0 if it's really 0 in most of the cases. So that's the procedure for entry identification. For pairing, we now have to build up our vector entry by entry. But I think the important thing is that, like, I just want to point out one thing, that we are always working with a candidate of S squared entries, because we are, if we sort of have the end in the jth step, we have identified the first j minus 1 entries of each of the active coefficient vectors, and there are S active coefficient vectors, so we have S sequences that can appear for the first j minus 1 coefficients. And so the candidates from which we then have to choose which are truly the active one are all the combinations of these S sequences that we have already identified and the S candidates that have been identified in the entry identifications. So I think I will skip the calculations again, using some energy estimates where you're asking the question, is this 0 or is this non-zero, and then keeping the largest one, keeping only O of S largest. So here, that's the procedure. As I mentioned, you are in the candidate set of the previously identified entries in the jth step and the candidates for the jth step, then we're getting a new set of candidates, pj plus 1. So that's as much as I want to give you for the idea of this. And I will summarize this in a theorem that basically says that we have a number of samples that is polynomial, we have a runtime that is polynomial in all these, with all the relevant parameters, and at the same time gives you an approximate reconstruction. So this was probably the most technical part. In the last part, I will talk about dimension reduction. And the idea is that we have many data vectors for some very large dimension. And the important thing here to point out is that we have no structural assumption, in contrast to what we've seen. No low dimensional structure, no sparsity, no manifold, no nothing. And then we want to do, nevertheless, do dimensionality reduction. So we would like a linear map such that the dimension, that the geometry of the set xj from j equals 1 to p is preserved under the embedding from xj to phi of xj. So if we plot this here, then I mean, this is very hard to depict because this only makes sense in very high dimensions, but the idea is that we have some lower dimensional subspace, and then we map all the elements to the subspace, and then the pairwise distances on the subspace should somehow be the same approximately as the pairwise distances in the full space. So this picture here is misleading because here we are really doing orthogonal projection, and of course then the pairwise distances will go down. So that's why you project and then you expand by some factors. So basically the hope was that in the projection you are reducing the pairwise distances by the same factor that you can then compensate by multiplying with an appropriate constant. So that nevertheless, we can write it down in this form here, this lemma that's first established by Johnson and Lindenstrauss. And I would even call it a theorem. That's why we call it like this here. So we have an arbitrary set of p points in n dimension. And then we're having a natural number, that's the embedding dimension, and then we're just mapping in this large dimensional space in this smaller dimensional space, such that the pairwise distances are approximately preserved. So the interesting fact is that the embedding dimension does not at all depend on the dimension of the space that you started in. So even if you have a very, very high dimensional space, this will not show up in general in this embedding. The only thing is that if you have a large number of points, then of course it must show up, because if you think of that you are having the vertices of the cube, then obviously it will no longer work like this. If you have the vertices in exponential number of points, then there's no way you can project it such that the dimensions are preserved. So that's why we need a factor of this type. So this has a lot of applications. The first one I mentioned in the beginning briefly is approximate nearest neighbor search. So it's a little bit interesting that if you have some structure that is underlying, so you say your data is following approximately a manifold, and you want to recover this structure, then nevertheless you want to use these agnostic algorithms first, because there is a manifold that you don't know that you want to find. How does it work? These algorithms often exploit the idea that a manifold locally looks linear and globally does not so much. So basically you want to approximate the manifold locally by a linear approximation, and then patch all these linear approximations together to get an approximation of the manifold. But for that, you first need to find out which are the local points and which are the points that are far away. Because obviously, if you have a sphere and you imagine a sphere, and doing a linear approximation over the full sphere gives you something that's not very meaningful. So that's why you need to know you have many points in high dimensional space. You need to find which are the nearest neighbors. Then the other one is what I also had as a fourth example in the introduction, is randomized principal component analysis. So the idea is that you have a matrix that is very large, but has a few very significant principal components. So in some sense, its singular values are decaying very quickly. And you then apply a singular value, a Johnson-Lindenstrauss embedding from one of the directions, and then you can do the principal component analysis on the reduced matrix, which is faster because of the smaller dimension, and get the right singular values correctly. And then once you have the right singular values, you can also compute left singular values. Or you can just turn it around and do it again, stuff like this. Then it's also related to low-rank matrix recovery in certain cases, and compressed sensing. If you don't have sparsity in a basis like we've discussed before, but in a redundant dictionary, this also plays a role. There's many more applications. In many applications related to learning, for example, this has been picked up in recent years. So this is it's a seemingly very basic, but apparently very important problem to study. But it's important that something that I have already mentioned in the description, that the Johnson-Lindenstrauss embedding should also be efficiently computable. Just that it exists doesn't really help us. Because, for example, if we're doing randomized principal component analysis and we want to apply a Johnson-Lindenstrauss embedding, and applying this embedding is more costly than doing the full principal component analysis in the end, then probably there's not much of an incentive to do that. And the other thing is, that's maybe in some cases it's also important that you want to avoid to have too much randomness, because generating random variables is also a cost factor that should be considered. And if you have a chance to reduce this, that can also be very valuable. So the appeal of doing it in a linear fashion is that it's, first of all, simpler in general, but there's, in particular, we can look at the set of differences between the points. Here it's called E, xi minus xj. And then we call what we wanted that f of xi minus f of xj is approximately the same as the left-hand side and the right-hand side here, the distances between the corresponding points. And if it's linear, then we can pull out this linear map, and then we have x minus j here, linear map times x minus j in the middle and x minus j on the right. And that's why when we give a name to the set of all these differences called E, we can write it as a relationship that only involves this x minus xj here, which we now call y. So the strategy is again via a union bound. So first of all, yes, we should mention that we are now in the second case, that the second way out, because we don't have any structure. So the randomness must just be used in a way that, like if I have a fixed deterministic embedding, there's no way that it can work for arbitrary point sets, because there will be points in the kernel where it fails. But we want to use a random construction here. And the simplest way to do this is via a union bound. So if we can show that for a fixed vector x, we have this embedding. In this case, we don't even have the discretization problem because we have a finite set in the first place. So we can start with our, just do a union bound over all the vectors in here. So if we have a probability of this form, then you can see that, let's just play it around what it means, because M is bounded by, we said this is bounded by some constant. I think log P over eta, or 4P or something, divided by epsilon squared was the formula that we had. And that's why if we plug it in here, you see that the epsilon squared exactly cancels, and then we get log 4p over eta or something like this. And this exactly gives you something along the lines of eta over p. And then you remember we want to do a union bound over p points. If you remember from the first part, the probability adds up. So we have p times eta over p or something, and that gives us the desired overall probability of failure eta. That's how we get a Johnson and Strauss embedding with high probability. That's the idea. And now I want to draw a connection to a concept that you've seen before in the first part, namely the restricted isometry property. So this is to recall. We have used it multiple times already in the second part. Let me just quickly recall it, that we're asking that our matrix phi would be scaling. If you apply it to a vector x, then the result that is k sparse, then it would be between 1 plus delta and 1 minus delta times the true norm. And so before we go and discuss how to do Johnson-Lindon-Strauss embeddings, I'm going to try to convince you that we have already done it. Because let's see what's the crucial concentration inequality that we have here. We have this is how it looks like. We have phi x greater or equal to 1 minus 8 epsilon times x 2 norm squared and 1 plus epsilon x 2 norm squared. And then recall how we proved the how we proved the restricted isometry property for sub-Gaussian random matrices in the first place. Then you notice that's exactly the same. So we have used exactly a concentration property of the form 7 in order to prove the restricted isometry property. So if you want, you can restate the result of Baranyuk and others that we have exploited in the way that if a matrix satisfies the concentration inequality 7 here, then you can even choose epsilon equals to deltas, absolute constants, and so on and so forth, then the restricted isometry property holds with these near optimal constants. So you can say the Johnson-Lindon-Strauss lemma implies the restricted isometry. On the other hand, it's maybe less obvious that this also works in the other way. So what I'm going to discuss in the remaining time of this class is that if you have a matrix that has the restricted isometry property, this also gives you a good Johnson-Lindon-Strauss. So of course this doesn't quite work because you know, even if you, because the restricted isometry property is a deterministic property, right? So as we said, no deterministic matrix can work generally as a Johnson-Lindon-Strauss, because otherwise you just take something in the kernel. Also, a RIP matrix will have something in the kernel, and then you cannot have a norm preservation on these vectors. So the trick is that you introduce some additional mild amount of randomness that's very easy to compute. Namely, you are introducing a diagonal matrix with plus minus ones chosen at random on the diagonal, and the diagonal matrix is very easy to compute. In some sense, you are really randomizing the column signs of your matrix, and that's already enough in order to assure that you get the restricted isometry property, provided that you have the Johnson-Lindon-Strauss property, provided that k is scaling logarithmically in the size of the set P. So you can think of this as a converse of the other result, because you can write it in terms of this concentration inequality 7. The result by Baranyuk said, if you have the concentration inequality 7, then you have the restricted isometry property. And here we're saying that if you're having this the restricted isometry property doing randomized column signs, then you get the concentration property 7 as well, and you lose at most one logarithmic factor in this respect. Okay. Before we go a little bit into how this is proved, let's see how this can be combined with some of the results that I've shown you in the first part. Because what I mentioned is, and here I have the right reference added by Havif and Regev as well. So if you take Fourier matrices and you randomly subsample them, you get k times log squared k times log n. and that's the restricted isometry property bound, and I'm leaving out all the absolute constants for the sake of presentation. And then here you plug it in, and then K should, if you recall, should be something like log P over eta. So you plug in log P over eta here, and then you have basically log squared, log of P over eta, and one additional log factor in the dimension. And in the case of the convolution, you have 4 factors, so you also get 4 on the right. Yes, there's a number of references that have been used there for these bounds. So what is important to state is that if we are using Fourier matrix or also convolution, then both of them have fast multiplication properties because of the fast Fourier transform. So just write it down. In particular, the non-equispaced fast Fourier transform. Okay. So I would now try to get you an idea of how things are proved here. So one trick that you're doing is we don't know anything about the vector, but we should also know that the restricted isometry property is something that is independent of the order of the columns. Right? We want something about every subset of every submatrix of S columns, or K columns. So it doesn't matter if I shuffle the columns, this property will be preserved. So if we're focusing on one particular vector, by shuffling the columns of the matrix, we might as well assume a certain order of the entries. And in this case, we are assuming that our vector is in decreasing arrangement. That is to say that x1 in absolute value is greater or equal to x2, greater or equal to x3, and so on. Right? Because we are really doing this for one vector and then doing the union bound. If we can establish this for one vector in this decreasing arrangement, then this is good enough. So then we are going and splitting the vector into blocks. Like we have ordered it according to the size, and then we are splitting into blocks that are all of length k over 2. So we start with the first block, that's the largest k over 2 entries, the second block, the second largest, and so on and so forth. And in some cases, we're using this notation x flat, because these are the large entries, and then this is, you can think of this as the flat part if we want to combine all the blocks except for the first into one long vector. Now let's do some computations. We have what we want to estimate is phi, our matrix, our RAP matrix, times d psi times x in the 2 norm squared. And then the important thing is a very important observation that is crucial to our proof is that applying a diagonal matrix with psi on the diagonal to a vector x is nothing but the pointwise multiplication of the entries of psi and the entries of x. So it's also the same as applying a diagonal matrix with x on the diagonal to the vector psi of these plus minus 1 entries. So we are doing this transformation, and then we're splitting it into the terms. We're doing 2 types of splits. The first is where, like when you can write this split this phi now also in the same types of blocks according to the ordering of x. And then you see that phi j is multiplied with dxj and psi j in the same order, because that's just how matrix multiplication works. The jth block of the matrix is multiplied with the jth block of the vector. And then we're using the fact that we are taking a square here. So this is the object that we want to estimate. So in the square, you can have the square of the jth block, that's this sum, but you can also have cross terms. And the cross terms we still distinguish. We have the cross terms where we have the product of the first block and some other block, so that's just the flat part. And we have the last sum here, the product of two blocks that are different, but that are both not consisting of the largest n. So that's the idea how we will proceed with the proof. Is this idea clear? Please interrupt and let me know if there are any questions. So the first term is the easiest, because we have just chosen the matrix to have the restricted isometry property, so we ignore the random signs completely and just say the block is defined to be a short vector. So we just switch the order of these two things back, and then notice that applying random signs to a vector doesn't change its two norm, so we could just apply the restricted isometry property to this vector here, and get that it's found above and below, because all the blocks are sparse, and in this case here we're only looking at the matrix phi applied to sparsity. So it's a direct application of the restricted isometry. And because we're having additional cross terms, we are choosing delta a little bit smaller than epsilon, namely epsilon over 4. So this is giving us the main contribution. So for the second term, we now have to use have to use the randomness, and I think I want to dive a little bit into what are the random tools that are used in these things. And one inequality that's very important is what's called Hoeffding's inequality. This is really coming up in a lot of places when you're having plus minus ones chosen at random, and you are you're considering the sum of these random signs with the entries of a vector. Then again, what you get behaves similar, has a scaling or a tail decay that somehow scales with the two norm of the vector. So in order to get the tail decay, if you think about, let's go back to the second term, it's written in a little bit of a different form. But here we can see this is the plus minus 1 term, this psi flat. So it's a very long vector. It's a long sum of plus minus 1s. So if we call this thing to be V, so we have really exactly an object of the form, or this is what V star then. So we have V star inner product, or V inner product with psi flat, which is exactly of the form that we have here, because this is V inner product with some psi's that are chosen plus minus 1 at there. And so what this lemma tells us, or this proposition, is that in order to understand this random variable, we need to estimate the two norm of the vector. And this is what's done in the following proposition here. that basically says if we have the restricted isometry property, then the vector v, which is exactly given as this here, just with a star, we're turning it around. So we're starting with dx b flat, x flat, phi flat, phi 1, phi flat star, phi 1, x1, and so on. And if you look, that's exactly what you have here. With the only difference is that we are ignoring, like here where it says b, we would have another amount of randomness. That would be the random coefficients corresponding to the first block. But we're ignoring this amount of randomness here because it's so few bits. So that's why we're just saying it's an arbitrary vector b plus minus 1. And then this proposition says that the 2 norm is bounded by something with delta over square root of s, which then allows to apply her. So how are we, what are we doing there with the different components? What are we going to do about this? So the key insight, and this is related to some, this has appeared in different related form in some other parts of the compressed sensing literature, is that the jth block can be bounded by the j minus first. So we have the decreasing rearrangement. And so let me try to convince you that this is the case. So, namely, all entries in xj are larger in absolute values than any entry in xj minus 1. This is, they are ordered. So, sorry, it's other way around. This should be j minus 1. This is j. All entries, no, just change it. So this is the j. They are ordered. The first, the block entries in the first are larger than the entries in the second, and so on. So all entries in xj minus 1 are larger and larger equal in absolute values than any entry in xj. Hence, also larger or equal than x. So the largest absolute value is just the infinity norm. So when it's larger than any entry, it's also larger than the infinity norm. And that is to say, so xj infinity. And now let's see what is the 2 norm. Xj minus 1 2 norm squared is the sum of let's say L in the support of xj in order to, this is the j minus 1 block, x L 2 norm squared, and this is so this here we're now using this property that we've just stated. We have just said any entry in, like all entries in xj minus 1 are larger than in absolute value than the infinity norm of xj. xj blocks, so we can write the same L in the support of xj minus 1, x j infinity squared. And now we have to see how many entries are there in this, because these are all the same. So the sum is just a multiplication by a constant. And this is equal, I think we said, k over 2 times, or is it k? It just changes constants. So if we have it like this, and so basically if we go up and we divide by k and take the square root, we get exactly what was here. The other thing, so that's the key part of the idea, that we have ordered them in order to be able to control one block by the previous. And then the off-diagonal RIP estimate, this is something that one needs to calculate somehow. So the idea there, I will just draw a picture. If we say this is block J union block L, then the union of the two blocks will have a support of 2k. So we will, and we know that we have the RIP. So if it's, we know that on this set, we will use the RIP condition to see that it is close. It is very, very well conditioned, so it's very close to the identity. So we're having something here on the diagonal and a lot of small things out here. And what we are looking at here is only one of these blocks, and because it's far away from the diagonal where all the action is, that's how you can see that it's small. And you can actually make this visualization pretty much rigorous in exactly the same way that I've just said. So, so I said RIP implies that action on diagonal and off diagonal small. So that's really what's happening here, what we're using. So that will be the second ingredient that we will use for the proof of the proposition. And so let me see that I haven't. I think I will go back and do it here. So now we can go and have a look at the V. So with these tools, estimate the two norm of V. So let me see. We have here what's V, and so we are now using again the implicit formalization of the L2 norm. Basically, we're taking it as an inner product over all vectors y with 2 norm equals to 1. That is something how you can characterize the L2 norm. So we have y, and because our vector v can be split easily into the blocks according to the the vector x, let's also split our vector y in the same way. So let's do a sum, and the important, we're splitting up the flat part here, and the flat part excludes the largest entry. So it's basically, that's why we are starting from L equals to 2 to R and having y. These are not, have nothing to do with the largest entries of y or something like this, because it's not the ordering of y, it's the ordering of x. But now for the other part, we can really just plug everything in, x star L here, phi L. Here we're having phi 1, and now we're flipping again dB and x 1. Okay, so this is this. So let's estimate the different terms here. The supremum remains 2 norm equals to 1. The sum remains, and we're doing Cauchy-Schwarz. With the 2 norm of the vector y. Now, let me ask you, so we have in this term here on the right-hand side, we are having the 2 norm of the vector x1. And now we have to estimate the action of all these matrices that we're having here in the spectrum. So let's write them down. Phi L 1, spectral norm 2, 2, 2, and dB 2, 2, 2, and here dx star. L. So now, like this middle thing here, is we just shown is less than delta. That is this, what I've just argued about the off-diagonal IRTG. So what we need is now these 2 diagonal matrices. So maybe I'm asking for some input here. Anyone has an idea of how we can estimate this, what's the spectral norm of a diagonal matrix? You can also type in the chat if you don't want to speak up. No? Okay, so what is the spectral norm is the largest singular value. And a diagonal matrix is diagonal, so it's the largest eigenvalue in absolute value. So what are the eigenvalues of a diagonal matrix? Maybe a simpler question. Yes, yeah, that was an answer. Thank you. The largest absolute value of the eigenvalues, well, of the eigenvalues of the entries of the diagonal, right? The eigenvalues of a diagonal matrix are just the entries of the diagonal, right? And the largest in here, thank you. The entries on the diagonal, like we have the diagonal matrix dxl star. So what we get is largest absolute value is just the infinity norm. XL infinity norm, and here also B infinity norm, and then the rest remains. Yes, okay. So, but now we yes, I have done an extra step here. I need some additional space. Now we have the supremum. Sorry. And now we have one more result that we wanted to use, and that was, if you go back, that was that the jth infinity norm of the jth block is 1 over square root k times the infinity norm of the j minus first block. And so basically this is exactly what we're applying here, 1 over square root k times al2 norm. And then this here, we have two more terms, infinity norm of this. B is plus minus 1. The infinity norm of vector of p minus 1 is nothing to say about this, just 1. And here, same, here's the largest entry to, so if it could be that most of the mass is in the largest entry, so we cannot say much more than bounding by 1. And so we have this. And now we can use binomial formula for this and see that this is the supremum of 2 norm y equals 1, L equals 2 to R. And we can bound the product by the average of the squares. So 1 over square root of k 1/2 times the YL2 norm squared plus 1/2 XL 2 norm squared. And this is less or equal to delta over square root of k. This is because both y and x are normalized. So 1/2 times the two norms are exactly there to 1. So this is how eventually, I'm not going to get into more detail, but this is sort of what we need to estimate. So now we can plug everything in, and that basically gives us control over this term. And then because I'm running out of time, I think I will not go into any more details here. The thing is, for these terms where both are not the first block. So then you need some more complicated probabilistic tool, which is the Hansen-Wright inequality, which is somehow a two-dimensional analog of Hoeffding's inequality, and you need to have some more complicated estimates that you need to do, but it's very much along the same line. We again are using these bounds where you estimate one block by the previous block in the block. So that is the last ingredient. Putting everything together gives you the results of the Johnson-Lewis transform. And I think that also gets me close to the end of the talk. And so let me close by putting the things into perspective once more that I have shown you over this this morning. The first, the very different role of randomness is, I think, what I would like you to take home from this. Namely, we started off by studying completely deterministic property. right? The restricted isometry property is something, once it holds, you can recover. And randomness is only used as a tool to establish this property because it's so combinatorially so involved that it's difficult to do it using other means. On the other hand, the Johnson-Lindenstrauss lemma used randomness as a key tool because the main feature is that we want to be data agnostic. And if we don't want to use property of the data set that we're having, then it's very difficult to do any deterministic algorithm because your data set might just be the one example where it fails. And that's why we're shifting our parameters to saying we want to be allowed to use an arbitrary data set at the cost of having a small probability. And then this high dimensional identification procedure for parametric PDEs is somewhat a hybrid because on the one hand, we are using this deterministic RIP property in the different forms, but on the other hand, we had these Gaussian random sums that we were considering. So some of the results that we have then are non-uniform in the sense. There's a difference. The first case, once you have the RIP, it works for all input sets, and here sometimes these methods, it still says that for any given input, it works with high probability. So it could be that it fails for different input, like it fails for different matrices, or the sampling sets the results are a little bit less strong, but on the other hand, of course, the setting is also much more complex. And I hope that sort of this message has gotten across. Maybe some of you will find a way to use randomness in combination with structure in some of the problems that they're facing. And if you have any questions of how the techniques might be useful to what you're facing, feel free to contact me and I will be happy to discuss.